Moving on from chapter 6 to chapter 7, we start talking about modeling, which is a powerful tool that helps us engineers understand, analyze, and improve complex civil engineering systems. It is the art and the act of creating equations for things that we are not 100% sure how do they look like. So we give them a mathematical form. So why do we model engineering systems? Because real world infrastructure is complex, uncertain, and often costly to experiment with directly. Models give us a safe, structured way to simulate reality without paying money as a bare minimum, helping us explain phenomena, predict outcomes, and optimize decisions before we build or intervene or do anything on the ground. To build a successful predictive model, we follow a clear 10-step process. First, define your goal. What do I want? What is my end game? And once the end game is clear, the path becomes clear as well. Then we need to gather good data. Good data gives us good results, right? So we need good, clean data that we are sure that have been conducted and collected ethically and authentically. And then identify what do you want to predict, the dependent variable, and then figure out which variables are influencing this dependent variable, which are the independent variables, and then choose explore your data, try to clean it, figure out if there is anything in it that requires uh, editing. And based on that, you select your final model shape. You can actually sense if the model is linear or nonlinear, quadratic, and so on, just from the shape of the data, or your exploratory data analysis or your ANOVA. So once you do these, you kind of figure out how your model would look like. And then eliminate weak variables and get rid of them so that they won't skew or affect your data. And usually these are ones with a p-value greater than 0.05, usually. Then you split the data 80-20 into training, where you make the equation, and testing, where you apply the equation on the to make sure that the equation is valid. Then you calibrate the model, as in, if there are ways to fine tune it, improve the R square, go ahead and do them. And finally, evaluate its final performance on an external data set or on a real world application. So, to understand variables, we have two main types. We have dependent variables, which is the output you want to predict, like cost, strength, travel time, you name it. And the independent variables, which are the inputs of the equations or the drivers, such as material type, time, or load. For example, let's take a pavement model. In a pavement model, crack length, the length of the crack in the pavement, might be the dependent variable. And the input would be, let's say, rainfall, traffic volume, or pavement age. Those are used or put in an equation to predict the crack length when it happens. Variables can take many forms. Continuous, like compressive strength, F prime C, which can be, let's say, 25.38 or 80.51, a decimal number. It can be anything, it's open ended. Whereas binary have are a discrete type of variable. They're generally in a box. So like pass or fail, yes or no, stuff like that. And categorical, like soil type. Soil type can be a silt or clay or silty clay or rock. So it's a category, right? There are various and different categories. Choosing the right model often depends on how your data is structured, what type of variables do you have, and how do you handle them. So that's very important that you handle them correctly. So once you have selected your variables, you need to choose a model shape. Will it be linear? Will it be quadratic? exponential? This choice depends on how your data is behaving. So plotting it first, and this is the thing we've been saying a lot, that plot your data first to see how it looks like, and then you can decide which is the best form for your data. And luckily now we have Excel that, the click of a button, you can see all forms together. So once you've developed your model, you need to calibrate it. And calibration means using your data to find the best fit line or curve mathematically. This means minimizing the squared distance between your predictions and the real values. In other words, improving your model and your equation to have a better R squared. So you can sketch it manually or use Excel or apply tools like Python or R in order to find the better fit model for your data set. The output is usually a regression equation, like the ones we did in class. Weight equals 2.43 times height plus 15.28. So this is one of the many techniques to really calibrate your model and find the better R square. And this is what you will do in your project deliverable 1 and then in project deliverable 2, where you will calibrate the model you developed in PD1 to get a better result. Once you have calibrated the model, how do you know if it is any good? R squared. R squared tells you how well the model fits your data. So if it is, in the 92% realm, I've been saying this a lot, 92%, it's like the sweet spot. So if it's in the 92% realm, generally you've hit the jackpot. Also, you can add to it t-tests and p-values. We said if something has a p-value above the 0.05, probably it is bad, so we get rid of it. Also, t-tests that are poor, that have very low values or negatively insignificant values, for example, are also a bad idea, and we try to get rid of them as well. So a model with a high R squared but nonsense variables is not useful. We need both. We need statistical sense and engineering sense. So I need to apply my engineering judgment to figure out if this equation is realistic as well. So you always have a role, even with all this technology, you always have a role to decide if what you're seeing should make sense or not. For example, you developed a new equation for moment that does not include the applied load. Well, that's weird, right? Because a moment is something reactive, so it needs to react to something. So you see what I'm trying to say here? It needs, although if you get a good R square and good statistical sense, there needs to be a good engineering sense. Many real world problems involve multiple variables. That's where multiple linear regression comes in. And that's what the main tool you should use in PD2. One dependent variable, but two or more predictors, right? Interacting with each other. It can be even quadratic or more. So in Excel, you can do that in just a few clicks in the data analysis tool pack that we've went over in the class. It outputs coefficients, R square, and p values to help you interpret the results. And that's mostly like multilinear regression is going to be the focus of your PD2, right? So let's recap. Modeling helps us engineers simulate reality with data. We have 10-step approach that guides us from question to solution to figure out a model in the end. And the model is only useful if it is statistically sound, good R squared, good B value, good T test, and it is practically relevant. It needs to make sense engineering wise. So that's it for modeling. We will do later on some problem solving, but this is the summary of the whole topic. So, repeat it as much as you need until you let the ideas sink in, and then we will do some problem solving.